Hi everyone, and thanks for joining us. We have actually already looked at permutations, but this time we're going to look at it a little more closely. Instead of ordering all the objects that we have available to us in a row, we're actually going to only choose a couple of objects and then only permutate those ones. Is there a formula to figure out how many permutations there are? Let's figure it out together by first looking at a simple example with 3 simple playing cards. And here we have the Jack, Queen, and King of Spades. As we've talked about before, a permutation means the number of ways that we can line these 3 cards up in a row. But permutation actually has another meaning. Instead of permutating all the cards that we have here, we can actually only choose some of them and then line them up. For example, from these 3 cards, let's look at how many 2-card permutations there are. Here's one permutation, Jack and Queen. Here's another permutation, Queen and Jack. Remember to switch the order, and remember the arrangements depend on the order. Another permutation, Jack, King, and yet another, King, Jack, and also Queen, King. And our final 2-card permutation for these 3 cards would be King, Queen. So in finishing up, the number of 2-card permutations we have for these 3 cards would be 6 permutations in total. Later on, we're going to derive a formula to actually figure out how we can get 6 without actually writing them all out like this. So we're going to come back to this example a little bit later on as example 2. So before we look at that, let's look at example 1, which is actually going to help us derive the formula for the number of permutations. Let's take a look at the letters A, B, C, and D. We are only going to pick some of the letters and permutate them, but we're not going to permutate all of them. We will at the end. That is what this entire lesson is all about. This definition of permutations is not choosing all, only some, and then arranging the letters. A. How many permutations are there for only one letter of A, B, C, D? So we're actually only going to choose one letter and write out how many permutations there are for that. So if we're only choosing one letter, the first case would obviously be just choosing and arranging A. There's only one way to do that. The second way would be choosing B, and there's only one way to do that. Let's choose and arrange C. There's only one way to do that. And finally, let's choose and then permutate D. Only one way for that as well. So there we have it. How many one-letter permutations do we have for the letters A, B, C, and D? 1, 2, 3, and 4. 4 permutations. B. Now let's look at how many 2-letter permutations there are. So we need to pick and arrange 2 letters each time. The first one will be A and B, and then we permutate them. 2 permutations, AB and BA. Now let's try picking 2 different letters this time. A, C. How many permutations would there be for A and C? 2, AC and CA. What other 2-letter permutations will we have? Seeing a pattern here, next I would choose A and D. How many permutations? 2, AD and DA. If you feel confident, please go ahead and try and finish performing. Those are all the permutations with the letters A. Now let's choose B and C. Next, B and D. And finally, C and D. So counting these all together, how many 2-letter permutations do I have for A, B, C, and D? There would be 12. 2, 4, 6, 8, 10, 12. 12 permutations. Getting tricky now. How many 3-letter permutations would there be for the letters A, B, C, and D? I think the best strategy is to cover up one letter each time and then permutate the ones you can see. Covering up D, that leaves me with A, B, and C. How many permutations are there for the letters A, B, and C? Well, there are 3 letters in a row, factorial 3, which would be 6. Let's see if we can write out those 6 permutations for A, B, and C. ABC, ACB, BAC, BCA, CAB, and finally CBA. Now let's choose 3 different letters this time. Let's cover up C, leaving us with the 3 letters A, B, and D. Let's write out all the permutations for the letters A, B, and D. Please go ahead if you can and get the answer before me. There we go. Still going. Let's choose 3 different letters again, this time by covering up the B. Covering up the B leaves us with the letters A, C, D. Let's write out the permutations for the letters A, C, D. And we get 6 again. And finally, we still have more permutations here. Let's cover up the A this time, leaving us with B, C, D. Let's write out all the permutations for the letters B, C, D. Whew. So I think we're done there. So how many 3-letter permutations do we have for the 4 letters A, B, C, D? We have 6 times 4, which is 24 permutations. Let's now take a look at the last one. If we are going to permutate all 4 letters, how many ways can we do it? From the previous presentation I did, that would simply be permutating all 4 letters in a row, which would be just factorial 4, which is 24. Let's write them all out. Please go ahead and try and write them out before me if you can. We should get 24. How did you go? Were you able to write them all out? I hope so. And the answer should be 6 times 4, which is 24 permutations. So our answers, we've got 4 and 12 and 24 and 24. That's kind of weird, there's no pattern there. So what we might do now is look at A, B, C again in a different way, and let's see if we can figure out some sort of a pattern or a formula for this permutation problem. So back to A. How many ways do we have to actually pick one letter and then permutate it in a row? We actually have a choice of 4. So the answer is 4. Okay, which agrees with what we have there. And B, if we are permutating 2 letters, how many ways can we choose and then arrange 2 letters in a row up there like so? That would be 4 ways to choose the first letter, and remember, and usually means multiplication in mathematics. There would be 3 letters left after choosing the first one, leaving 3. Now let's look at C. To choose the first letter, we would have 4 choices. Then 1 letter is gone, there are 3 left. And now 2 are gone, now there are 2 letters left for our third choice. 4 times 3 times 2. And D, for the first letter we have 4 choices. And then 3 left, 3 choices. And then 2 left, 2 choices. And then finally there is only 1 letter left to choose from. 1 permutation for the last letter. So looking at our answers when we write them like that, can we see a pattern? Yes, we're starting to see something appear, aren't we? But to me, it still isn't quite clear what exactly is happening or whether or not there's actually going to be a formula for this mess. But you know what these things remind me of? Factorials. Maybe we can use factorials here somewhere and see if we can make sense of all this rubbish. Let's look at B. What I'm going to do is I'm going to add a couple of factorials here, strategically placing them, and actually try and uncancel something, and then see if we can develop a pattern that way. I'm going to turn b into a fraction, and then I'm going to multiply the top and the bottom, numerator and denominator, by factorial 2. It's still the same number, right? So that is not going to change the size of the number. It's just going to make it look different. Those factorial 2's will simply cancel out. But writing it like that, maybe we can notice some sort of a pattern happening. We can now write the answer for b as 4 times 3 times factorial 2 is simply factorial 4 on the numerator, and still the factorial 2 on the denominator. Let's look at c and do the same thing. Only this time I'm going to multiply the top and the bottom by factorial 1. So that's not going to change it, it's just changing the way it looks. This expression can now be written as factorial 4 on the numerator and factorial 1 on the denominator. Let's now go back and look at a now. Doing the same thing for a, I'm going to multiply top and bottom by factorial 3. And this can now be simplified to factorial 4 over factorial 3. So now we can see a bit of a pattern here. Factorial 4 divided by factorial 3. Factorial 4 divided by factorial 2. Factorial 4 divided by factorial 1. And d, we haven't done yet. That must be factorial 4 divided by, let's follow the pattern and do the same for d. That must be factorial 0. We know that factorial 0 is 1, so the top is factorial 4. And the bottom is factorial 0. Factorial 0 is 1, this is okay. So definitely we can see a pattern, but we're still not quite there yet. A, we have 1 letter, but it's factorial 3. B, we have 2 letters, factorial 2. Well, that matches. C, we have 3 letters, factorial 1. D, we have all 4 letters in factorial 0. So what we notice is this number and this number always add to 4. 1 plus 3 is 4. 2 plus 2 is 4. 1 plus 3 is 4. So to get this pattern looking very, very obvious, I'm just going to make one last adjustment. For A, instead of writing factorial 3 on the bottom, I'm going to write factorial 4 minus 1. For B, instead of factorial 2 on the bottom, I'm going to write factorial 4 minus 2. For C, instead of factorial 1 on the bottom, I'm going to write, you guessed it, factorial 4 minus 3. And for D, instead of factorial 0 on the bottom, I'm going to write factorial 4 minus 4. And there we have it. Can you see the pattern now? Yes? If you can't, let me make just one little adjustment. How about now? Does that green help? You can now see the pattern, and the number of letters we are permutating, and how that actually affects the final answer. And these 4 final expressions here are actually the formula. And when you need to use the formula, it is actually displayed like this. When we are permutating one object out of 4 objects, it is written as 4p1. And the one I'm going to write in green, like so. And the same for B, that would be 4p2. Likewise with C and D. C, the answer is 4p3, and for D, it is 4p4. In this P notation here, the blue number represents the number of objects we have to choose from, and the green number is how many of those objects we are actually only going to choose and then arrange in a row. So now let's take a look at this P formula in a little bit more detail. So if we have n objects available and we want to choose and permutate r objects from those, the total number of permutations is nPr, which is given by factorial n divided by, and then you subtract r from n, giving n minus r, and the factorial of that as well. And P, of course, means permutations. And there are also some alternative notations for nPr. As I've said here, it's nPr with the N and the R low down. But there are others, written like this, with the N high, the N and the R both on the right side of the P, and also N and R in brackets, kind of like a function notation with two inputs. Which of these notations should you use? Well, it depends on maybe who's teaching you or which book you're learning from. Just whichever one that you see in your resource, that's the one you should use. When I was at school, I actually used nPr, this one with the N high. When I was at school, that wasn't too long ago.
Yes, that was very, very long ago.
Wasn't that long ago? I'm not that old.
Yes, it was that long ago, and you are that old. Face it, you're just not young anymore.
Let's move along. And also, this can be done on the calculator. On your calculator, hopefully, you should be able to find a button that has one of these on it. Once you've figured out how to enter it into your calculator, you can calculate nPr for any values of N and R. Let's just briefly go back to example 1, and using this formula, let's see if we agree with those answers. So now that we are familiar with the nPr formula and how to get the answer on a calculator, maybe you should go through A, B, C, and D by yourself and just convince yourself that these answers are correct. Is 4p1 actually equal to 4? Is 4p2 actually equal to 12? Do you agree that 4p3 is equal to 24? And lastly, is 4p4 equal to 24 as well? And while we're here at D, this is actually a good time to just reinforce why factorial 0 is actually equal to 1. For the formula to work, factorial 4 divided by factorial 0 must equal 24. Factorial 4 is 24. So for this to work, factorial 0 must be equal to 1. And that is one good explanation as to why factorial 0 must equal 1.
This is probably a good chance to explain that the nPr formula can also be used to determine the number of ways to arrange n objects in a line.
If I have n objects to choose from, and I'm actually going to choose all of them and arrange them in a row or a line, then the answer should actually be factorial n, right? But I can use the permutation formula to get that same result. That would simply be, instead of choosing r things, I would be choosing all n things. nPn. Applying the formula, that would be factorial n divided by factorial n minus n. N minus n is 0. And we all know that factorial 0 is 1. Which gives us factorial n as we expected. So that agrees. When permutating n things from n things, we are just going to get factorial n, the number of ways to arrange n objects in a line. Now let's try example 2. We're going to do our Jack, Queen, and King problem again. And this time we're going to use the formula and verify that we get the same answer. So how many 2-card permutations are possible from these 3 cards? The Jack, Queen, and King of Spades. We have 3 objects, so that would be our n value. And we are choosing to permutate 2 of those objects. That would be our r value. So our answer would be 3p2. Applying our nPr formula, that would give us factorial n divided by factorial n minus r. 3 minus 2 is 1, giving us factorial 3 divided by factorial 1. And the method used to solve this is to try and cancel out the factorial on the bottom by doing this. Writing it as 3 times 2 times 1 factorial, and then the 1 factorials cancel out. Leaving us with 3 times 2, which is 6 permutations, which is what we got earlier on when we did the problem.
6 total permutations.
It agrees. Here when we cancelled out the factorial ones, that did look a bit silly, but I'm just showing you the process we use to actually get the answer. And from here on in, I may actually just skip this first part. I'll just go from here straight down to here. The 3 minus 2 will give us 1. Don't really need to write that out once you get used to it. Let's move on to example 3. In how many ways can a president, a secretary, and a treasurer be decided from a committee of 7 people? This is a permutations problem because we are assigning labels to the 3 people. We're basically giving them ranks, or we're ordering them. So from 7 people, we are going to choose an order 3, so the answer is going to be 7p3. Using the formula, this is factorial n divided by factorial n minus r. N is 7, r is 3, n minus r is going to be 4. To cancel this out, let's rewrite factorial 7. Factorial 7 is 7 times 6 times 5. And then from here on in, we can simply write factorial 4. And the denominator, still factorial 4. Now we can cancel out factorial 4. This leaves us with 7 times 6 times 5. 7 times 6 is 42 times 5. I might do it this way. 6 times 5 is 30. That's easier. 7 3s are 21, so 7 times 30 is 210. So there we have it. From a committee of 7 people, the total number of ways to assign a president, a secretary, and a treasurer is 210 ways. Let's try another example. In how many ways can first, second, and third place be decided in a race with 8 swimmers? Here we are assigning ranks, first, second, and third. So obviously this is going to be a permutation problem. 8 swimmers in total, that will be our n. And we are going to choose an order, first, second, and third. 3, so r would be 3. So the answer is going to be 8p3. I think this number is going to be kind of big.
Okay, I'll let you use your calculator for this one.
Oh, thank you. That's really nice. 336. So in a race of 8 swimmers, there are 336 total possible permutations for first, second, and third place. I hope you feel like a little bit more practice because here are examples 5 and 6. In example 5, you have 6 books on a shelf. In how many ways can you choose and read 2 of those 6 books? Is order important in example 5? And example 6, in a game of musical chairs, there are 9 children playing, but there are only 7 chairs available. And those 7 chairs are actually different chairs, by the way. Is that important? How many ways can those 9 children rush to sit down in those 7 chairs once the music stops? And there's only 1 child per chair. Can they use their calculators for these questions?
I'll let them use their calculators for example 6 only.
That answers that. Feel free to share your answers in the comments, and thanks for watching.